Homework 4.1, Exponential Functions, Video 4. So now that we've talked about what an exponential function is, how to use your calculator, and some exponent rules, let's talk about what these exponential functions graphs actually look like. So we're going to start by graphing an exponential function whose base is greater than 1. And you may recall from the definition of an exponential function that the base has to be positive, but it can't be 1. The main reason is if it's 1, then the output is always 1, and it's just a constant function f of x equals 1. So we exclude that, although technically it's a exponential function, it loses a very important characteristic, namely the fact that it fails to be invertible at that point. But let's graph f of x equals 2 to the x by using the original old-fashioned graphing technique. Stick in some x's, spit out some y's, and see if the graph emerges. And at the end of this, we'll draw some conclusions so that we don't have to replicate the table process every time we want to sketch the graph of an exponential function. Okay, so let's input 3 into this function and see what we get. If we put 3 in for the exponent, we get 2 to the third power. That's small enough we don't need a calculator, but you're welcome to use one, and you would get 8. So one ordered pair on this graph would be 3, 8. As if I didn't anticipate that. Over 3 and up 8. Let's put a red dot up there. So there's 3, 8. Okay. And the rest of this goes pretty smoothly. In fact, let's go ahead and fill out all of these, and then we'll move them all over to the graph, to the coordinate plane. Just for clarity, a graph is what you draw. The coordinate plane is the space on which you draw it. Okay, so 2 to the second power is just 4, nothing to look at there. If we put 1 into the function, we get 2 to the first power, but that's just 2. But then we start getting to ones where exponent rules start becoming an issue. For example, if we put 0 in, then we get 2 to the 0 power. And again, instinctively, most people just want to say 0, except anything to the 0 power is 1, as long as the base isn't 0. Plus, it makes sense if you look at the outputs here and notice that as I move down this column, the outputs are getting cut in half. Half of 8 is 4, half of 4 is 2, half of 2 is 1. And then when we start getting to the negative exponents, if we were to just capitalize on the pattern where we're taking half of 8 is 4, half of 4 is 2, half of 2 is 1, half of 1 is 1/2, or we could use the exponent rule that says any number raised to a negative power is the reciprocal of that positive power. So in this case, 2 to the negative 1 is the reciprocal of 2 to the positive 1. Of course, 2 to the first power is 1/2. Another way of looking at it is this value is the reciprocal of that one. So guess what 2 to the negative 2 power is? Well, 3 ways to look at it. Keep cutting in half, use this rule, or 2 to the negative 2 is the reciprocal of 2 to the positive 2. No matter how you look at it, it's going to be 1/4. And so it shouldn't surprise you that 2 to the negative 3 power is going to end up being 1/8. So let's see what happens if we put these dots up here. Okay, 2, 4, over 2, up 1, 2, 3, 4. Not much to go on there. 1, 2, over 1, up 2. If you just look at it casually, you might think it's a straight line. A line. Straight line is redundant in algebra. All lines are straight in algebra. There are topics where that statement is not true, but this isn't one of them. Okay, but if we put the next point 0, 1, that gives us a y-intercept here, and now it doesn't look quite as linear. It looks like we're getting some curvature here. And of course, that point is 0, 1. Now, as we start venturing into negative exponents, our outputs keep getting cut in half. So when we go back to negative 1, we're only up 1/2. So negative 1, 1/2. When we go back to negative 2, we're only up 1/4. So negative 2, 1/4. And by the time we get to -3, we're barely off the x-axis because we're at -3, 1/8. So yeah, this thing bent and suddenly it's trying to get horizontal. Let's connect these smoothly. I think I know what's happening over here. The right end is rising. This is blowing up really fast. But what's happening on the left end? Well, we could crank out more dots for evidence, but let's think about what's happening here. As we move from right to left and hit each integer on the x-axis, each point is, its y value is cut in half. So as we keep going, these points' distances from the x-axis are keep getting cut in half, so they get closer, but they never actually touch it. Oh, wait a second. We've seen this before. What do you call a line that a graph gets closer to but never touches? That's an asymptote. So it looks like we have a horizontal asymptote at y = 0, but only on the left half. So I guess it's a half asymptote. It sounded funny in my head. And there we have it. We have the graph of f of x = 2 to the x power. And honestly, this will always be the graph when the base is greater than 1. If the base were different than 2, for example, if this were 3, then as you're moving from left to right, instead of all the heights doubling, they would be tripling. Now this would still be at 1 because 3 to the 0 power is 1. But if the base were 3, then it would get 3 times as high, and then 3 times as high, and then 3 times as high, so it would grow a lot faster. So, what can we say in general about the graph of f of x = b to the x as long as the base is bigger than 1? And by the way, the reason the base is bigger than 1 is because if it were less than 1, multiplying by a number less than 1 over and over makes the number smaller, not larger, as you'll see in the next video. So, if the base is greater than 1, then the graph of f of x = b to the x, and let's just list some properties. Let's start with the y-intercept. The y-intercept is 1. That's easy because anything to the 0 power is 1, as long as the base isn't 0. There's no y-intercept, there's no x-intercepts because of the asymptote. Horizontal asymptote on the left is y = 0. We could also write that using arrow notation as x approaches -infinity, f of x approaches 0. However, the right end rises, so we could say as x approaches infinity, then f of x approaches infinity. What else can we say? This graph is increasing. We mentioned that briefly back in chapter 2, but increasing means as you're going from left to right, the y values are getting higher. And this graph is increasing all the time. It's a very slow increase at the beginning, but then it takes off. Let's talk about domain and range. The domain, well, it goes forever to the left and forever to the right, so the domain is -infinity to infinity. But what's the range? Well, it goes up forever, so the range goes towards infinity. But it does not go down forever. How low does this graph get? Well, it gets closer and closer and closer to 0, but it never equals 0. So parentheses. So this is an example of a range that has a number to start it, but doesn't include it because of the horizontal asymptote. I keep thinking there's one more feature that I'm leaving out. I can't think of it. Oh, it's not really a feature, it's just an FYI. If your function is generic, f of x = b to the x, then this point is 1 comma b, because b to the first power is b. So if it were 3 to the x, then the point would be 1 comma 3. If it were 10 to the x, it would be 1 comma 10, and this thing would grow really, really, really fast. Oh, the other thing I meant to say, it wasn't that. This is referred to as exponential growth. Any physical phenomenon that's modeled by an exponential function does this. And what exponential growth means is the growth starts out slow, but it's slowly picking up speed, and eventually it skyrockets. There are several physical phenomena that demonstrate exponential growth. One of them you may have heard in the news is the spread of a disease. People like to say that this represents the number of people that will catch a disease if it goes unchecked, but the truth is, the spread of disease is not an exponential growth, because exponential growth increases without bound. There's not an infinite number of people in the world, so at some point that growth would have to slow down. Initially, it's exponential, but honestly, the spread of a disease in a population is modeled by something called logistic growth. Look it up if you're curious. It starts like this, but then it has another horizontal asymptote when it starts reaching the total population size. But other things grow exponentially. Well, the one that's probably most important to you is investments. If you have money that you invest and it grows a certain percent per year, your money grows like this. The growth starts out slow, but over time, the growth rate starts speeding up. So if you plan to retire, you should invest as soon as possible, because let's say that this graph represents the growth of your investment, and let's say this is a 40-year time span. So you start planning for your retirement when you're, say, 20. But let's say that that first 10 years that you work, you decide, I don't want to invest, I'll just wait in 10 years to start planning for my retirement. If you cut 10 years off of your investment, guess which end you cut it off of? Not the beginning, but the end. So cutting off that extra 10 years could lose that amount of money, whatever that scale is. So if you learn anything from this class, it's that if you're going to invest for your retirement, you should do it as early as possible. Now, honestly, retirement doesn't work just by putting down money and walking away. You add to it each month, but the growth aspect is still the same, that the sooner you can start planning for retirement, the bigger growth spurt you have at the end. So take that to the bank, literally.